Hello, everyone. My name is Akash, and I'm a postdoc fellow at TU Berlin. I've been working for past 6-7 months or so on this work with Professor Holger Stark at Institute for Theoretical Physics. First of all, I would like to thank the organizers for the opportunity to present my work, which is nonlinear dynamics of microswimmers in inertial and viscoelastic flows. So small microbes like bacteria cannot generate large thrusts like us while swimming. To propel their bodies, they resort to periodic deformations, such as this carpet-like structure over their body. They deform it, and in order to move themselves forward. During this process, the flow field that they generate reminds us of a source dipole, provided that the density of the fluid matches with that of the microorganism. In a similar fashion, a bacteria can flap its flagellum in order to move forward, but the flow field would be fundamentally different in that scenario. And recently, there has been a thrust towards developing artificial microswimmers, which can be tuned to go back and forth. But they still rely on the mechanism is still close to the low Reynolds number motion. We are interested in analyzing the dynamics of microswimmer in ambient flows because such systems are ubiquitous in biological environments, and recently experiments are being performed in microchannels to understand their separation and biofilm formation and so on. And furthermore, it gives us insights into reproductive system, as to recent work has shown that sperms are capable to move against the flow field in order to fertilize the egg completely via hydrodynamic interaction. So one of the first models was devised by Zoertel and Stark in 2012, where they wrote down the equation for dynamics of microswimmer in a pressure-driven flow, where they write that the rate of change of displacement, which is velocity, is equal to the swimming velocity plus the unidirectional parabolic flow velocity. And the rate of change of orientation is governed by the vorticity in background flow. What they found was that the system was analogous to a simple pendulum, and also that if the flow was weak, which means the ratio of the fluid to the swimming velocity is less than 1, then the swimmer has the tendency to go upstream. If not the case, then swimmer drifts downstream, but it can select among the tumbling and the swinging states, again depending on the initial condition. This was backed by a simple linear stability analysis around the center line, which shows that the eigenvalues are imaginary. So what we find is that the system is degenerate, and also that the swimming mechanism is irrelevant here, because the system just needs the speed. But both of these things will change if we deviate from the ideal Stokezian model, which is the motivation of the work. So we are interested in this because the microchannels or the flow inside the microchannels can have certain effect of inertia, and also the biological systems or the biological fluids do not obey Newton's law of viscosity, so they can have their own polymeric stresses. So we are interested in finding the effects of these weak non-linearities. And there has been a recent work by the group of Yeomans in 2016 in their PRL work, where they showed that by taking hydrodynamic wall effects into account, and also the passive cross-stream migration, which results from the non-linearity due to viscoelasticity, they found interesting results. But we argue in this work that there is an additional component which is missing, which comes because of the self-propulsion, so which we will delve into more detail in the coming slides. One thing we want to clarify here is that we are working in quasi-steady limit. So the time scales of undulations of the swimmer is not very fast, so that the particle Reynolds number doesn't show up. And this has been recently taken into account by Redelli et al. And this corresponds to one of the examples of copepods. They produce certain thrusts to propel themselves forward at very high speeds. So we are interested in this quasi-steady system, which should give us the nonlinear effects, which will have both passive and active components. And the rate of reorientation will also have some modifications, but we have verified that these effects do not alter the trajectories of the swimmer qualitatively, so we have not accounted for them. Now let's take a look at the effect of finite fluid inertia. It is known from some time that a passive particle inside inertial flow experiences lift forces which can focus it to equilibrium positions. And this physics has been used to separate cells in biological liquids. So now to capture this nonlinear effect, what we do is we take the system of a passive sphere inside a pressure-driven flow, and we write the Navier-Stokes equations. And now to decide whether to use regular perturbation or singular perturbation technique, we first take the ratio of inertial to viscous forces, which tells us that that ratio is distance dependent, which gives a constraint on the domain size. So if domain cannot be larger than this Oseen radius. So if we follow this constraint, we can use the regular perturbation analysis. That's what we do. And we use the reciprocal theorem to find the lift force. We have plotted that here with the channel width here. And we see that the force or the equilibrium force vanishes at 3 locations. In this video, we don't see the central equilibrium position because it's unstable, as the positive slope identifies. Now we try to find the effect of swimming inertial lift, which is the second component which comes because of the element of self-propulsion in the problem. To do that, we find that we can make the approximation of unbounded flow, so we neglect the wall effects, and that brings in the error of order kappa, which is dispensable for the current purposes. And we can assume the swimmer to be like a paramecium, so we take the source dipole flow field which is characteristic of it. Now the question is that what regime will provide the leading order contribution? Will it be singular or regular? And we can use a simple order of magnitude analysis to find that out. So a singular lift will be of order of magnitude of the characteristic velocity, which we know is 1 over r cube. So if we substitute the Oseen radius from the previous discussion here, we find that the singular lift will be of power 3 by 2. So if the Reynolds number is much less than 1, then the regular lift is the larger one. So we can use, we should use the regular perturbation analysis to get the leading order contribution. So we use that with the reciprocal theorem, and we find an analytical expression of the problem. So now let's compare the two lifts which we have obtained for the inertial case. So the passive lift has the cubic profile and the swimming lift has a linear profile, but when we plot the total lift, we see that the total lift can change based on the orientation of the swimmer. So the equilibrium positions can shift if the orientation is changing, which it will under the effect of vorticity in the flow. So now we can find the total lift and we can substitute that in our dynamical equations. So we find that r dot equals the swimming plus the flow plus this nonlinear passive effect plus the nonlinear swimming lift effect. And the rate of change of orientation is primarily governed by the vorticity in the background flow. Now a simple linear stability analysis of these equations will tell us that now the real part of eigenvalue or the approximated eigenvalue is dependent on the two parameters kappa and Vm. So we can plot a phase diagram which shows us that there are two regions where we can find stable, centerline stable trajectories and centerline unstable trajectories. So now we also do the complete simulation of a neutral swimmer and we plot the phase diagram here. On the y-axis, we show the swimmer size to the channel size ratio, and the x-axis is the the flow speed to the swimming speed. And we find that if the ratio is less than 1, then the swimmer again can go upstream, but it will focus at the center line. So that's why we call it stable upstream. But if the flow speed increases, it cannot go upstream, so it goes downstream, which is shown in these trajectories here. No matter where the swimmer starts, it gets attracted to the center line. Now, if we take a look at the swimmer of this size, kappa 0.25, we see that as we go further, as we approach the unstable regime, we come across a supercritical Hopf bifurcation where we see growing limit cycles and which we call a swinging state, which is given in this figure here. The blue and the black trajectories are the one which tells us that the system is attracted to a limit cycle. And if we furthermore increase the flow rate, we find that the swimmer or the limit cycles again bifurcate into further two more limit cycles, which we call smaller tumbling cycles, which again reduced with the increasing flow rate, which is given here. So no matter what the initial condition, the system is attracted to these tumbling cycles either here or below, depending on the initial condition. Now we have another state at kappa 0.05 where the swimmer of smaller size will undergo a subcritical half bifurcation. So what we see here is that around Vm equals 10, it will approach a stable plus tumbling state, which is shown here, that depending on the initial condition, it can either take tumbling state or the centerline attraction state. But nonetheless, if we keep increasing, the system will ultimately approach the tumbling state. Now, we have also done the same analysis for a pusher-puller or a bacteria type of swimmer, which has the forced dipole flow field. And we find that the singular lift in that scenario would be order REP. So, which is the same as the regular perturbation technique. So one can use either of them to get the leading order approximation to the lift. And that's what we do. We use a regular perturbation with the reciprocal theorem. And we can no longer neglect the wall effects, because the error of neglection goes logarithmically. So it diverges with a distance. So we take wall effects into account using method of reflections here. And once we do that, we find the swimming velocity, so the swimming lift, which is given by this quadratic expression. And the total swimming lift now varies as this. Now this is fundamentally different than what we obtained for a neutral swimmer. So what we conclude here is that swimming lift depends on the style with which the swimmer swims. And also now we can take this into account, or put this in our dynamical equations, which is I've done here, along with the hydrodynamical effects of the walls. So we have velocity equals the swimming velocity plus the nonlinear lifts, which is the passive and swimming lift, and also the wall effect due to self-propulsion. And even here we have taken, in the orientation evolution, we have taken vorticity and wall effects to change in vorticity. So now what we find through a phase diagram, that for a puller, let's say, that if the flow strength is weak, then the puller is attracted to the center line, because it is known from previous works that pullers are generally attracted to the center line. So what we see is that hydrodynamic effects push the puller towards the center, whereas if the swimmer size decreases, then it can attain swinging states, as is shown here by the pink trajectories. In the case of pushers, we see that here the system will again have a swinging cycles, but they will be of larger magnitude. These lines here show the limit cycles when there is no wall effect taken into account, right? If now we change the flow speed to more than 1, we see that for both pullers and pushers, we have downstream swinging states. And if we change it furthermore, the tumbling states appear for both pushers and pullers. So this analysis we have published or it is accepted in the communications physics. So please check it out for more details. And the take-home message here is that, like swimming lift, the dynamics also depends on the swimming style. Now let's take a look at how the swimmer dynamics changes if we make the fluid viscoelastic. Now, like the previous case, we would expect that the passive and active component both should contribute to the swimmer dynamics. And that's what we see. So the passive lift is nothing but the normal stresses induced centerline migration. And to find the active lift, we assume the fluid to be following a second order fluid model, which assumes the viscosity to be constant and it extracts the weak effects of elasticity. So now following the previous framework, we find the passive and the active lift, and when we plot the trajectories of the swimmer, we find that both upstream and downstream are centerline stable, and this is consistent with the linear stability analysis that we do. Now this was also done, a similar work was also done using a second order fluid model by Yeoman's group, and then they did not take the active lift into account. They just took the known passive lift into account, and they showed that it goes to the center line. But what we think that will happen is, if we take swimming lift, this focusing time decreases dramatically. As you see, for low flow rates, you have very small focusing time if you take the complete model into account. And we can also show this over a wide range of particle sizes, that generally the focusing time decreases when we take this additional component into account. We also did the analysis for other types of swimmers, such as pusher pullers, and we got this paper accepted recently into Soft Matter, so please check it if you want more details. So in conclusion, I would like to say that the element of self-propulsion generates rich dynamics because there is a swimming lift in both these nonlinearities that we have explored. And we also find that the wall interactions can counteract the lift if they become larger. Next, we want to find the effect of elongated microswimmers and also going furthermore in the rotelet dipole, so not just relying on the far field description of the flow field by the swimmer. Thank you for your time, and I would like to thank Humboldt Foundation for supporting my postdoc, and you can use these QR codes to access the publication. Thank you.